Hey, this is Sean McCord, and this is my cryptography learning project. Um, the main idea behind this project is to implement encryption algorithms as a learning tool in C Sharp. My main target audience is future students who have to learn cryptography related stuff like encryption algorithms, and stuff like that. And the main reason I went with this project idea is because as a student myself, I feel like a lot of the times we learn about encryption algorithms, we usually gloss over the details on how they actually work and the actual mechanics that makes these encryption algorithms function. So my main goal is to provide an in-depth understanding to future students who want to learn about encryption algorithms. The main encryption algorithms I'll be using are the data encryption standard, advanced encryption standard, elliptic curve cryptography, and RSA. The first two being symmetric encryption algorithms, and the last two being asymmetric encryption algorithms. Um, Another goal is to provide a means to compare the algorithms to each other. So, whether that be their security, their speed, overall performance, I wanted to include a way for users to be able to compare the algorithms to one another and see how they perform under different circumstances, such as, how does this encryption algorithm work whenever my text file is really big or really small? Like, which one is faster under what particular circumstances? I have a list of functional requirements for my project. I wanted to build it in C Sharp because I'm pretty familiar with how C Sharp works, and it makes compartmentalizing stuff into classes pretty easy for object-oriented programming. Uh, and because I wanted to use C Sharp, I went with Windows Presentation Foundation, which is kind of like a newer, more advanced version of Windows Forms, which I'm a little bit familiar with Windows Forms, and I've gotten familiar with WPF as I've worked on this project. At first I wanted to have a minimum of AES and DES encryption because I wasn't entirely sure how complicated it would be to get all of these encryption algorithms implemented. I think I at first overestimated how difficult it would be to get all this implemented, and so far I've gotten not just the two symmetric algorithms, but also the two asymmetric algorithms implemented. Also, like I said earlier, I want to be able to provide metrics for the students to compare encryption algorithms to. So one of those metrics is speed. I want users to be able to encrypt and decrypt their own text files and have them be text files as big as the user wants. Um, And initially, I wanted to explain how the algorithms worked in the output, along with the output text file whenever they use it. But I feel like a better way to approach that would be to have a separate page that explains all the encryption algorithms that we're working with. So I'll probably end up implementing that in a different way than how I have it listed here. I'll probably go with a separate page for that. Obviously, I want decryption functionality. You want users to be able to encrypt stuff and decrypt it. Um, and an additional goal is to potentially improve the algorithms in various ways. Um, One example would be the security related to DES is known to be outdated, and it's relatively insecure and compared to the other ones. So one way to improve that would be to increase the key size through triple DES. Um, and there's also just general speed improvements and reducing bloat on the algorithms. So my required resources, like I said earlier, I'm using C Sharp and Windows Presentation Foundation for my UI. Um, Additionally, C-based languages, I've noticed, have pre-built encryption libraries, um, which makes it really easy to use certain encryption algorithms where you don't have to implement the whole thing by yourself. I've decided not to use these because it kind of defeats the purpose of showing students how these algorithms actually work. So instead of using these libraries to outsource kind of all the work to a different place, I kind of wanted to implement everything in house. Um, so that's kind of how I've been implementing these algorithms so far. I do use the some standard built-in libraries within C Sharp, just none related to cryptography. And they're mainly used for user interface building, data handling, file handling, just the standard stuff. I included this in my previous presentation, but I did want to include it here so I could kind of circle back to that object-oriented design aspect I was talking about earlier. As you can see in that picture on the right, I have all the encryption algorithms implemented as a class and tied together in the main window.saml.cs file to the user interface. Um, so not only is it just good coding practice to do something like this, but also if the students in the future wanted to go into the code themselves and see how everything actually is put together, they can easily find where everything is. And that includes in the user interface. I have it separated out through comments to show where certain algorithms start and end in the main window.xaml.cs file. So I went with kind of a segmented philosophy on this so that students can more easily find what they're looking for. Some current cryptography trends. I mentioned this last time, but post quantum cryptography is blowing up right now, especially. Um, and basically, what that means is that the increased processing ability of quantum computers can basically crack a lot of the encryption algorithms used today. The main one to worry about, though, would be RSA. That one is the most vulnerable to quantum computers because it has a theoretically possible way of cracking RSA. Exists a possible way to crack RSA using quantum computers. And now that Microsoft, as of a few weeks ago, has come out with the first quantum computing processor, the Major Honor 1, this is even more of a concern now, especially. Another trend is homomorphic encryption, and this is basically allowing operations to be formed on encrypted data. So this would be useful for people who want to be able to access stuff and change data without actually decrypting it. Uh, so, for example, like credit card numbers or something like that on a bank database, for example, like instead of having to decrypt it to work with that data, you'll be able to work with it while it's still in its encrypted form, so that at no point is there ever any chance of exposure of that encrypted data. And there's also ongoing standardization and regulation efforts from the government and National Institute of Standards and Technology related to encryption, especially now that quantum cryptography is kind of taken off, or quantum computing is taking off. I feel like this will be a major effort in the future. So far this semester, I've focused on the asymmetric algorithms. Last semester, I finished up the symmetric ones. So I started with RSA this semester because I figured it would be a little bit easier conceptually to implement than elliptic curve cryptography. It's not uh, a super foreign concept to me like elliptic curves are. Um, and it relies on the difficulty of factoring large prime numbers. So it's a little bit more simple conceptually, in my opinion. And The second algorithm I worked on this semester is, or so far this semester, is elliptic curve cryptography. And this is another asymmetric algorithm, but it uses elliptic curves and the discrete logarithm problem to provide security using smaller keys. Um, so yeah, let's talk about RSA. Like I mentioned a second ago, uses the complexity of factoring large prime numbers. Um, in my code, I use 512-bit prime factors P and Q, and I use those with the public key to generate the private key. Um, and I randomly generate the prime factors using a method I'll talk about here soon. Um, but the main idea is that the private key is generated through several mathematical principles that I had to kind of get used to. You can see down there, D is the private key I'm referring to, and it's generated by finding the modular inverse using the public key and another variable called phi, which is derived from the prime factors. And I go more in detail on the math here soon. Uh, like like I mentioned a second ago, the prime factors are generated randomly using my generate prime function. Um, I initially had a bit of an issue with this because uh, the way I was generating it was causing my program to crash because I didn't have a like a max on how many attempts it would run. It would run it um, so many times to try and generate a prime that it would just crash my program. So I had to implement a set number of max attempts so that it would stop crashing it. And that was mainly due to the way I was checking if a number is prime. The initial way I was doing it was kind of basic, and it wasn't working well with large um, prime numbers. It wasn't working well to test super large numbers if they're prime or not. So to fix this, I did a little bit of research and came up with the Miller-Robin primality test, and this managed to fix my issue of program crashing. Here I have a snip from the Wikipedia page on the Miller-Robin primality test, and this kind of goes through how it works. Essentially, you pass a number that you think is prime to this test, um, and it will essentially test it against other random numbers between 2 and n minus 2. Um, and it will do that so many times, and for each time it passes, we count that as contributing towards primality. And if it fails, then it fails a primality test. So, like I mentioned a minute ago, I have the generate prime running for a max of 1,000 attempts. So and the way I'm generating the prime is it's able to find a prime value in the set number of attempts, and if it doesn't find if the Miller-Robin primality test doesn't find a prime value, it'll cut it off there and generate another number and test it again. And it will do that so many times until we eventually get an acceptable number. The second algorithm I worked on this semester is elliptic curve cryptography. Um, this was honestly a little bit easier than I thought it was going to be. I thought that this would be super hard to get working. Um, and I mentioned earlier it uses the mathematical complexity of the discrete logarithm problem, which is essentially if you have 2 points and a scalar set up in that equation, as you can see in that first bullet point, it's infeasible to find the scalar given those 2 points on the elliptic curve. Uh, the main hurdle with this algorithm was the strangeness behind elliptic curve arithmetic. So the operations used to generate the public key, the private key, and the shared secret all hinge on elliptic curve arithmetic, like adding points to each other, multiplying points, and dividing points. And it's pretty strange to try and get used to that. Um, but well, I'll mention that here in another slide. But I went with something called elliptic curve Diffie-Hellman approach, and it uses the shared secret generated from the public and private key to create a symmetric key for encryption and decryption. And since I already had AES implemented last semester, I figured I'd go with this, make it a little bit more simple. Um, with elliptic curve cryptography, there are a bunch of different curves you can choose from. I chose the SECP 256K1 curve, which is it's the curve Bitcoin uses for their public key cryptography, and it's pictured there on the right. But essentially, that just defines what our curve parameters are going to be uh, for the elliptic curve. So there's set parameters, and defining those based on what the curve that we're using plays a big role in generating the keys. I mentioned this on the last slide, but elliptic curve Diffie-Hellman is a hybrid encryption approach. So it uses the shared secret made from elliptic curve cryptography to create a symmetric key. As you can see in the bottom picture there, that's the function I'm using to create an AES key from the shared secret. So I pass the shared secret as a parameter to this function, and it takes the first 16 bytes of the um, of the x coordinate of the shared secret because it's a point on the elliptic curve, and it takes the last 16 bytes of the y coordinate of the elliptic curve or of the shared secret, and it combines that into our AES key. And we then use that and pass it to the AES function that I implemented last semester to encrypt and decrypt our data. I talked about this earlier, but the elliptic curve cryptography arithmetic is pretty strange. It was a little bit difficult to get used to because of the way it works. As you can see on the left hand equation, these are from the Wikipedia page on elliptic curve arithmetic. But that left equation represents finding the slope whenever you're doubling your points, which is already a little bit strange, but that the division here is actually because of the properties of elliptic curves. I'm not sure why exactly it works like this, but with elliptic curve points, division is the same as multiplying by the modular inverse. So it was a little bit strange to try and implement this because of just how weird the math was. And that formula on the right, or those equations on the right, represent adding two different points to each other, how to find the value of the third point. And it was just really odd. Uh, I implemented the double and add method for multiplication, and I use these equations here for the add points method, which is important for generating our keys. Here is a picture of my elliptic curve cryptography page. I added a couple things since the symmetric algorithms, because of the way asymmetric algorithms generate keys rather than the user choosing them. I implemented some buttons for the user to be able to save and load keys to um, to basically allow them to reuse keys whenever they want. Uh, Here you can see in the bottom left my public and private, or my public key coordinates, which is a point on the elliptic curve. And I included an extra text box below the buttons to show the specific curve parameters of the SECP 256K1 curve, which those curve parameters can vary depending on which elliptic curve you decide to use. But I implemented that partially because I wanted the user to be able to see what the curve parameters were, but also because I was having an issue where it was parsing p, and at whenever it was parsing p into a big integer, it would put a negative value for some reason. It was causing a whole issue, so I included this so I can make sure the parameters were initialized correctly. In conclusion, my future plans are to fix any issues I have with the existing algorithms. Um, I also plan on improving my existing algorithms, like I mentioned earlier with the triple DS, and including speed and security improvements. Since I have all the algorithms I plan to implement, in the program, it should give me a lot of time to work on algorithm improvements and various other improvements for the project. Uh, I also plan on improving the UI to streamline some places in the program, implement that learning tab like I mentioned earlier, so that users can have a centralized location to see how all the algorithms work in one place. And I also wanted to finish the metrics section for all the algorithms so that users will be able to compare them to each other, and add a separate metrics page so that they can see all that in one place. Anyway, that's the end of this presentation. If you have any questions, don't hesitate to reach out.